This presentation is about the principles and interpretation of Hess screen and other dissociative tests like the Lees and the Lancaster red-green test. The primary position is probably the most important position of gaze. We can measure the angle of deviation in the primary position using different methods such as prism and cover test, and then conclude that this patient has left hypertropia of 25 prism diopters and left exotropia of 15 prism diopters. But what would we do if you want to know the eye alignment in different positions of gaze? One easy way is to photograph the patient in all 9 diagnostic positions of gaze and to put a graphic portrait of the alignment in these positions. We can also write down the muscle responsible for the movement of the left eye in each of these positions. This way, one can tell that the greatest deviation is in the field of action of the left inferior rectus muscle with the greatest amount of hypertropia, indicating a problem in this gaze direction and in this muscle. Another way we can measure the angle more accurately using an objective method like the prism and cover test, and again plot the measured angle in each of the 9 diagnostic positions. Again, you can see that the largest deviation is in the down and left gaze, suggesting a problem in the left inferior rectus muscle. One last way is to represent the right eye with a red dot and the left eye with a green dot, and to plot the positions of the right and the left eyes in the 9 diagnostic positions using these red and green dots. Again, you can see that the green dot, which is corresponding to the left eye, is higher than the red dot, which corresponds to the right eye, particularly on looking down and to the left, indicating a left hypertropia that increases in this field. These green points corresponding to the left eye can also be connected together using straight lines to plot the field of movement of the left eye. When we put the 4 figures adjacent to each other, one can see how similar are the different plots to each other. And if you also wrote down the muscle acting in each different gaze direction, this would make the interpretation a bit faster and easier. But the question is, how can we get this nice portrayal using red and green dots? The Hess screen and other dissociative tests are subjective tests that are based on the patient's perspective of the difference in the position of images seen by both eyes. The more the horizontal deviation, the farther apart will be the horizontal displacement of the 2 images. And the more the vertical deviation, the farther apart will be the vertical displacement of the 2 images. These tests depend on 3 physiological principles, which are projection, normal corresponding retinal points, and simultaneous perception, which is a crude form of binocular vision. The first physiological principle is projection. Projection simply means that the brain assumes the actual position of objects in real space depending on where the image will fall on the retina. So if a patient is driving a car, for example, and the retina received 3 images, the brain will assume that the car is on the right side, as the image of the car fell on the left part of the retina, that the tree is on the left side because the image of the tree fell on the right part of the retina, and that the deer is in front of him because the image of the deer fell on the macula. This can be demonstrated easily using the synoptophore. If the image of the cage fell on the left part of the retina, the brain will assume that the cage is on the right side. And if the image of the cage fell on the right part of the retina, the brain will assume that the cage is on the left side. And if the image of the cage fell on the fovea, the brain will assume that the cage is in front of him. The second physiological principle is the presence of corresponding retinal points. We know that the image falls on the retina as an inverted image. If the eyes are well aligned, the image of the head of the snake will fall on the nasal retina of the right eye and the temporal retina of the left eye. The image of the tail of the snake will fall on the temporal retina of the right eye and the nasal retina of the left eye, while the middle of the snake will fall on the fovea of both eyes. The points where the same image falls on both eyes are called corresponding retinal points. Therefore, the maculae of both eyes are corresponding retinal points, as the image falling on the fovea of one eye should fall on the fovea of the other eye. The third principle is simultaneous perception. Simultaneous perception refers to the ability of the brain to see with both eyes at the same time. So imagine if the image of the cage is on the fovea of the right eye and the image of the bird is on the fovea of the left eye, since the image of the cage falls on the fovea of the left eye, the brain will assume that the cage is in front of him. And since the image of the bird fell on the fovea of the right eye, the brain will assume that the bird is also in front of him. With simultaneous perception, the brain will see both the bird and the cage at the same time and in front of him, so the brain will assume that the bird is inside the cage. So how do we use these principles in order to plot the eye alignment? We present two different targets or images, one to each eye. We dissociate the two eyes to ensure that each eye sees only one target at a time. If the patient has no misalignment, the image will fall on the fovea of each eye, so the brain will think that both objects are in front of him and superimposed. If the patient has an outward deviation of the left eye, for example, now the image of the bird won't fall on the fovea, so the brain will assume that the bird is not inside the cage, as its image did not fall on the fovea. The patient is asked to move the photo of the bird until its image falls on the fovea. Once the image of the bird falls on the fovea of the left eye, now the brain will think that both images are in front of him and that both images are superimposed. We can make use of this movement to measure the angle of deviation. The larger the amount of movement required, the larger the angle of misalignment. The Hess screen is one of the dissociative tests that depends on dissociation of both eyes by placing a red filter in front of one eye and a green filter in front of the other eye. These red-green filters are usually called Armstrong goggles. The patient is shown a red target on the screen while he is holding a green target in his hand. The patient is asked to place his green target on the red target on the screen. The red eye is the fixing eye, and we are plotting the field of the eye with the green filter. The patient is usually seated about half a meter from the screen, with the head erect and immobile using a chin or headrest. The examining room lights are dimmed to remove fusional background cues and to further dissociate the two eyes. This is usually sufficient to reveal a well-controlled heterophoria. We start in the central gaze. A red target is shown in the middle of the screen. The patient is pointing a green light from a special type of torch in his hand called Foster torch. The patient is asked to place his green light over the red light that he sees. The test is then repeated in different directions of gaze. The test is then repeated, but after turning the goggles so that now the green filter is placed before the right eye and the red filter is placed before the left eye. Now we are plotting the field of the right eye. The patient's response is then recorded on a piece of paper and the points are connected together to draw the Hess chart of the patient. Now let's understand, what does the patient actually see and how does the brain interpret it? The patient is asked to look at the central red dot. The patient's right eye is the fixing eye. By that we mean it is the only eye seeing the red dot. The patient's left eye cannot see the red dot. The patient is then asked if he can see the green dot. The patient will be able to see the green dot only with his left eye. The patient's right eye with the red filter won't be able to see the green dot. If the patient has some exotropy of the left eye, the green dot will fall on the temporal retina, not on the fovea. So the patient will think it is on the nasal field, not in front of him. The patient is then asked to move the green dot to be exactly on top of the red dot. The brain will now think, the image of the red dot is on the fovea. This means that the red dot is in front of me. So I am going to move the green dot until it falls on the fovea of the left eye. Once the image of the green dot is on the fovea of the left eye, the brain will assume that it is also in front of him. This means to the brain that both the red and the green dots are exactly in the same place. The more the divergent the eye, the more the patient will have to move the green dot until it falls on the fovea. In other words, the position of the green dot on the screen shows the direction of the fovea of this eye. If the eye is hypertrophic, the green dot will be deviated up, and if the eye is hypotropic, the green dot will be shifted down. The test is then repeated in different directions of gaze. This way, one will be able to know the position of the left eye at each position of gaze in respect to the right eye. Then we repeat the same test after exchanging the red and green filters to now test the position of the right eye in each direction of gaze in respect to the left eye. One has to remember that in order to get accurate results from a screen, the patient has to have good vision in both eyes, to have some simultaneous perception, as well as a normal retinal correspondence. The head screen is plotted with the letter L indicating the field of the left eye and the letter R indicating the field of the right eye. The test is done for both the central and peripheral fields. The central field plots gross displacement in alignment, while the peripheral field plots minor displacement in extreme gazes. At 0.5 meter test distance, each small square represents 5 degrees or 10 prism diopters displacement. This means that the inner square plots the central 15 degrees. This is about the range an individual will normally move his eyes to view a target away from the primary gaze without moving his head. The next step is how are we going to interpret Hess screen. The first thing you should look for is to compare the sizes of the field of both the right and left eyes. The eye with the smaller Hess screen is the eye with the primary pathology. In this patient, the field of the right eye is smaller. This means that the primary affection is in the right eye. In this patient, the field of the left eye is a bit smaller than the right eye, indicating that the primary affection is in the left eye, while the right eye is showing the secondary sequelae. The second thing you need to look for is the central dot. The central dot indicates the position of the eyes in the primary position. In this patient, it is obvious that the primary pathology is in the left eye, as it is the eye with the smaller field. When we look at the central dot of the left eye, we see that it is inferiorly displaced. This means that the patient has left hypotropia in the primary position. In this patient, the primary pathology is in the left eye, as it is the eye with the smaller field. Notice that the central dot is higher. This means that this patient has left hypertropia in the primary position. In this patient, the central dot of the right eye is displaced medially. This means that the patient has right esotropia in the primary position. And in this patient, the central dot of the right eye is displaced down and out, indicating that the right eye is exotropic and hypotropic in the primary position. In this patient, the central dot is in place, indicating that the patient should be orthophoric in the primary position. The next thing you need to look for are the edges of the vertical lines. If the lines are parallel, this means that the patient has no pattern. If the lines are sloping, this means that the patient has a V or A pattern. If they are sloping down, this means that the patient has a V pattern, while if they are sloping up, this means that the patient has an A pattern. Another thing that you need to look for is the presence of underaction and overaction of the extraocular muscles. In a patient with a normal medial rectus muscle function, for example, the line corresponding to the medial rectus will not be displaced. If the patient has underaction of the medial rectus muscle, the eye won't be able to reach the correct place, so the line will stop short before where it should be. On the other hand, if the patient has an overaction of the medial rectus muscle, the line will exceed the correct place. The next question we need to answer is the cause of underaction is present, whether paralysis or restriction. The first clue to answer that question is the central dot. If the patient is esotrophic, the central dot will move inwards towards the dot labeled the medial rectus. In paralytic lesions, because the deviation in the primary position is usually large, the displacement of the central dot will be large. In restrictive lesions, because there is only minimal misalignment in the primary position, the displacement of the central dot will also be very minimal. If the patient has a paralytic lesion affecting the medial rectus muscle, for example, one will see an underaction of the medial rectus muscle. And because this is a paralytic lesion, one will see an overaction of the direct antagonist muscle, which is the lateral rectus muscle, that is almost equal in magnitude. This will result in simple displacement of the square corresponding to the eye movement in different gaze direction, without compression or change in the shape of the square. On the other hand, in restrictive lesions, while the patient will develop an underaction of one muscle, there will be no overaction of the direct antagonist. This will result in compression of the square rather than just displacement. So to sum it up, in restrictive lesion, there is only a minimal displacement in the primary position, there is no overaction of the direct antagonist, and this will result in a compressed or disproportionate field. On the other hand, in paralytic lesions, there is significant deviation in the primary position, there is an overaction of the direct antagonist muscle that results in a displaced proportionate field. Next are some examples for different lesions. We will start with restrictive lesions. As we previously mentioned, the right eye is the eye with the primary pathology, as it has a smaller field. There is limitation of elevation of the right eye in adduction, consistent with an inferior oblique deficit. The cause of this limitation is a restrictive lesion for two reasons. First, there is no overaction of the direct antagonist muscle, which is the superior oblique, and this causes a compressed field. Second, there is no misalignment in the primary position, again consistent with a restrictive lesion. So now we are looking for a restrictive lesion in the right eye that is causing a limitation of elevation in adduction. The first thing that would come to our mind would be a Wright-Brown syndrome. In this example, the left eye is the eye with the primary pathology, as it has a smaller field. There is limitation of elevation of the left eye in abduction consistent with a superior rectus deficit. The cause of this limitation is restrictive for two reasons. First, there is no overaction of the direct antagonist muscle, which is the inferior rectus muscle, and this causes a compressed field. Second, there is only a small misalignment in the primary position, again consistent with a restrictive lesion. So now we are looking for a restrictive lesion in the left eye that is causing limitation of elevation in abduction, such as dysthyroid ophthalmopathy. In this example, the left eye is the eye with the primary pathology, as it has a smaller field. Notice that there is limitation of both elevation and depression of the left eye in abduction, with no overaction of any muscle in the left eye. In addition, there is only minimal misalignment in the primary position. This suggests a restrictive lesion causing limitation of both elevation and depression of the left eye, such as a fracture floor with an inferior rectus entrapment. In this case, the left eye is the eye with the primary pathology, as it has a smaller field. Notice that there is limitation of abduction and adduction of the left eye with no overaction of any muscle in the left eye. In addition, there is only a small esophoria in the primary position. This suggests a restrictive lesion causing limitation of both adduction and abduction, such as a left Duane syndrome type 3. Next are some examples of paralytic lesions. In paralytic lesions, one should look for other muscles equally. In addition to underaction of the paralyzed muscle, one can see an overaction of the direct antagonist and yoke muscle, and an underaction of the contralateral antagonist. In this case, the right eye is the eye with the primary pathology, as it has a smaller field. Notice that there is limitation of abduction of the right eye, but with overaction of the direct antagonist, which is the right medial rectus muscle. This causes the field to be shifted medially rather than being compressed. This suggests a paralytic lesion causing limitation of abduction of the right eye, such as right sixth nerve palsy. You can also see an overaction of the yoke muscle, which is the left medial rectus muscle. In this case, the left eye is the eye with the primary pathology, as it has a smaller field. Notice that there is limitation of depression of the left eye in adduction, suggesting a left superior oblique underaction. There is also an overaction of the direct antagonist muscle, which is the left inferior oblique muscle, thus suggesting a paralytic rather than a restrictive lesion. Finally, there is also an overaction of the yoke muscle, which is the contralateral inferior rectus muscle. Finally, Hess screen can be used to measure the subjective angle of misalignment. At 50 centimeters distance, each small square corresponds to about 5 degrees or 10 prism diopters displacement. There are other tests similar to Hess screen that are based on the same principles. The Lancaster red-green test is one of these tests. It is similar to Hess green, but uses a vertical streak of red and green light rather than a circular spot of light. This allows detection of subjective torsion in each direction of gaze. The test is similar to Hess green, but it is only done in 9 points. At each point, the position and the orientation of the streak is plotted. Another test is the Lees screen. The Lees screen is less dissociative than the Hess screen because of the greater contrast between the tangent screen and the background. In the Lees screen, two independently illuminated perspex tangent screens are positioned 90 degrees to each other. A double-sided plane mirror bisecting the screens is positioned at 45 degrees between the two screens. Each eye sees only one screen reflection from the mirror. The examiner points on a point on the illuminated screen. The patient is asked to point with his pointer at the same point on the non-illuminated screen. The examiner illuminates the non-illuminated screen temporarily to see and plot the patient's response. Another test is the Harms tangent screen. The Harms screen is a large screen measuring about 3 meters in each direction. It shows a chessboard pattern with the degrees of graduation extending across the screen. A fixation light is housed in an oblong bar in the center. The fixation light can be converted to a fixation line when testing cyclotorsion. This bar may be rotated 360 degrees using a motor drive and a remote control. The patient is seated 2.5 meters from the screen. A helmet with a fixation device is worn on the patient's head. This helmet projects a white cross on the screen. The examiner can use this cross to position the patient's head in any gaze position, usually about 25 or 30 degrees from the center. The fixation light is illuminated in the center of the screen. A red filter is placed before one eye. The patient holds a large handheld device to project a green ring onto the screen. The green ring is viewed only by the uncovered eye. The test is performed in a darkened room, which contributes to the dissociation. Thank you.